Hello everyone. So we are again with another interesting tech talk on virtual threads. So we have with us N M Bazlur Rahman, who is a senior software engineer with over a decade of specialized experience in Java and related technologies. He is officially recognized as a Java champion and has been deeply involved in a community outrage where he has been a moderator to Java user group in Bangladesh since 2023, and he has been an eminent speaker at various international conferences and Java user groups where he's actively talking about virtual threads, and concurrency. He is also serving as an editor of Java Q at InfoQ and Fuji.io, some leading platforms for technology content. So first of all, thank you, Bazlur, for taking your time for us, and we welcome you to this group and
Thank
information.
you. Thank you, Aditya, for your nice introduction. Let's start. And as you can see, the title is Virtual Threads, ushering in a new era of concurrency. And we all know that we have recently got the JDK 21. And JDK 21 comes with the virtual threads, and virtual thread is the most anticipated features of Java. We have been talking, the community people, I mean, all the Java developers are pretty much excited about these new things. I'm also super excited about it. Last couple of especially it started with JDK 19. There was a preview feature, and then 20, and finally it arrived on 21. So yeah, it was super exciting. The journey is also super exciting because it started long way back. One of the reason why Java is popular, we all pretty much know that concurrency, or the way of we can write threads in Java was the probably the most what can I say, most important, or the main reason, I would say, for Java being popular, so popular, right? And I don't know if you know that the concept of the user mode thread or virtual thread was in fact in the early release in Java 1. I can, as far as I can remember, they used to call it green thread, but then somehow they dropped it, the idea. But now we have a huge requirement for this, and finally it has arrived, and we are so grateful and excited about it. So I have given you a bit of background, and I'll add a bit more, and then basically I have a two-part over here. So one is basically a bit of background, why it's required, and then secondly, what it is and how we can, how it can help our day-to-day programming life. So that's the two-part mainly. And if I have time, I'll try to give you an idea of how it was implemented, basically the mechanics, internals. You guys pretty much already know about that, this, which is Java. We can in fact say that Java is made of threads, right? In all layers of Java programming, we use thread. Now the question gets to be, what is basically a thread? And thread is basically a unit of programming, unit of execution. For example, you write a code, it gets executed, right? So a block of code is executed by a thread. So you can say thread is basically an execution environment. And more threads means more execution environment. So if we have a program have more threads, basically it can run simultaneously a lot of things, and it gives a program responsiveness. And in some cases, for example, in web application, this is the way we achieve throughput of applications, right? So it's good that if we have more threads, we have more interesting thing we can do with our program. All layers of Java, for example, the way we use exceptions collect all these statements, and we debug all those things, right? If what went wrong in a particular area of code, and that's we debug those through exceptions. And exceptions are means of thread, basically. we run a program in a thread, and when thread we put everything on the stack. Basically, thread has a stack, right? All this call stack, and we collect all of those and we print them. Then there are other things, debugging, profiling, and all layer of Java. And if you can see, this is the main program, right? It doesn't have a lot of things. It's just one line, which is system out println. But if you if you see, there are multiple threads are already running over here. And this particular main method is executed by a thread called main thread. So even though if you don't directly write thread programming in your day-to-day life, you are definitely dealing with threads. So we can confidently say that the threads are all layer in Java platform. I just same thing. This is how we create threads. We can just create an instance of thread, right? We can pass the lambda expression on runnable, whatever you like, the way like earlier when before Java 8 we used to pass the runnable interface. Now we can just do lambda expressions, which is easy. I can show you a quick demo. Okay, so not this one exactly I intended to show you, but let me remove this one. There is another one over here. Okay, it's not even clean. Okay, never mind. I'll just create another one. Okay, can you see the screen? The code.
Yes.
Yeah.
So how do we create threads? It's pretty simple, right? We give a name. So let's say T1, and then we create instance of thread, right? And in the constructor, we pass a lambda expression. This is how we basically create threads, right? So whatever we pass over here, it's going to be executed by our new threads, right? So if I say hello everyone, then this hello everyone is going to be executed by our brand new thread, right? And if we want to test it, we can just print over here thread.current thread. Then we'll be able to see the name of this thread. So this one, so over here, this curly brace, it is the main thread is started from over here, and then it sees the few line of code, which is basically we instantiate a new thread, and then inside this, whatever in this code is going to be executed by a new thread. The job of main thread over here is basically instantiate the T1, and then we definitely maybe have to give a name, set name. We can identify differently. So JEP Bangalore, let's say thread, and we definitely have to start, right? Start, and we definitely have to join. So we'll wait to finish this particular one from the main thread. And that's it. Basically, that's how we create a new thread. And if you can see the output, it will take some time. Yeah, you can see we have a new thread whose name is JEP Bangalore thread, right? So this is how basically we create threads. And there are other ways. Obviously, we use thread polls. We definitely don't use create threads manually. But in the even though if we use let's say executors framework, we will probably in the background we're gonna create the threads the same way like this one. All right. So one thing we have to keep in mind is I'm gonna move. I'm gonna skip this slide just to make a point. If I put a breakpoint and let me debug it, try to debug it. Let's see what happens. Let's see. There should be a image to take a thread dump. I don't know why it's not showing over here. Idea had a icon over here that way we can just dump the whole do the thread dump, but I'm not sure why it's not showing. For some reason. Maybe if I do a thread.sleep, probably it may. So let's see if I do a thread.sleep for a long time. Let's see if it works. So All right. So this is the long time, and let's see if I can see the icon. Sometimes it shows the icon, sometimes it doesn't. I don't know when it does and when it doesn't. It still doesn't show. Probably let me see if I can find this. Never mind. It's just just bear with me. Some as I said earlier, live coding always go wrong in many ways. Anyway,
particularly with concurrency, it always happens like this.
So what happens is if you take the thread down, you will see something like that basically. So you just focus about the there is a thing called TID and NID. NID basically is our Java. Java gives the ID to a particular thread, and this one is basically given by a operating system. What it means is, when we create a threads using our Java construct like new threads, Java doesn't create threads. Java thread is basically a wrapper of our native threads. What it means is it basically requests operating system to give us a thread, right? Creates a thread. So operating system basically, take care of creating threads and maintaining threads, scheduling threads. Java doesn't do anything. Java just, asks it. It's a basically one-one mapping. So I have a Java object so that I can, work with it. And with the Java thread, operating system has a thread, and operating system and Java thread has a sort of one mapping. So that's what happens. That's what I basically wanted to show you. But just hear me out. Anyway, so moving on. Now, what's the problem? We can create threads, right? We can create a lot of them, and simultaneously we can make our program, in a program we can create a lot of them, right? So we can put different piece of code in different thread, and it becomes interesting, especially if it's a web application. What happens is when I receive a request from a client, I pretty much give this responsibility to that thread. So let's say that's what happens in web server application, right? So when we get a request, we hand over that request to a thread, and we get another request, we hand over that request to another thread, right? So that's what happens in traditional web application server, unless you use something else fancy, for example, reactive. But we're not going into that area. For now, let's focus on the traditional web application. So a request comes, you give that responsibility to a thread. The problem is threads are expensive, and there are many ways it's expensive. For example, it takes like 2 megabytes of memory outside of the heap, and also scheduler. The operating system has a scheduler to schedule those threads, right? Because not all the thread runs all the time, right? So what happens is if my computer has a, let's say, 10 core, so at a point of time only 10 thread runs. So what scheduler does is basically it has some sort of algorithm. For example, it could be round robin, or it could be some sort of priority preemptive algorithm. It depends on operating system, which operating system you are using. Let's think about it's a round robin. It could be different. That's not a point which algorithm it's the particular operating system used. So what it means is if I have thousands threads at a point of time in my computer, not all of them are running all the time, right? Only, let's say this computer has 10 core, so 10 of them are running at a point of time. Then operating system basically switches them. It gives a particular thread for a period of time, let's say 100 milliseconds, not 100 milliseconds. I'm just saying it could be like 10 microseconds. It could very small amount of time, and then it switch so that everyone gets their fair share. And when this context switch happen, it takes some times, right? It has some overhead. So that means if I have like millions of thread in my computer, that will also take a lot of memory, right? And then the context switching would be huge because the operating system would be always busy to switch one thread to another. So these are the problems. So, and also there are other problem is the number of thread we can create in a what do we say? How can I say? In a operating system is limited. It's a constraint put by the operating system. We cannot create an unlimited amount of thread. For example, if you want to create 1 million threads, we'll not be able to do that. There is always a limit. Threads are limited and expensive. Our modern web applications cannot achieve high throughput that our modern web application requires. We want to, for example, a particular web server, maybe we want to get high throughputs because we have a lot of users. Like for example, one particular server has 2 million users. If they hit at the same time to a particular server will not be able to survive, right? But if we have a lot of threads, we could probably able to help them. So what I'm trying to say over here is the throughput is limited by the number of threads we can create. So that's the problem. Let me show you a quick demo how many threads we can in fact create. The traditional thread we can create. So I'm gonna try this demo, but again, bear with me. Something can go wrong. So what I'm gonna do is I'm use a counter over here. Atomic integer 0. While true, I'm gonna run a while loop, and I'm gonna create a new thread. Var t. So basically, I'm gonna create a new thread, and I'm gonna increment the number. That's it. Let's say the number is now count. And I'm gonna do a print over here so that I can see how many already I have created, right? So if counter, I'll print only when thousands of them are created. Otherwise, it will be a lot of noise in the console. Count we have created. Okay, so what I'm gonna do is once I have done that, I'm gonna just park this thread. So basically, block support. But so this thread will be created and stay there and will not do anything else. And I'm going to start this thread basically. So what is basically I'm doing is I'm letting this program to create unlimited amount of thread, and when I see how many threads we can create. So let's see. You can see. So we were able to create around 16,000 threads, and then we received this out of memory error, unable to create native threads, possibly out of memory. So there is a constraint, right? We cannot create unlimited amount one, obviously not a million one. And this number varies based on operating system your resource available. For example, this computer has a 64 GB memory, so that's probably why it was able to create this many. But if you have a computer with less RAM, probably you will not be able to create this many. So the idea is threads are limited. We can create only a few thousand perhaps, and that's why the web applications, that the kind of throughput we want in our modern application probably not possible by because we're constrained by the number of threads, and also it is expensive. Also, yeah, there are many reasons. So how do we the same thing basically over here. Moving on. So we got this out of memory. Okay, so I'm going to skip this one as well because I showed you the demo already. So now the problem gets problem. So these are the problems with the current system. We have a limited number of threads, and that's why we have a, we are constant by it, and we cannot achieve high throughputs for modern applications, which is required because we now have a lot of data sensitive and cloud programming and all those fancy things, and a lot of users are continuously hitting our server. We want to serve them better, and again, so what we do is we have come up with lots of interesting ideas. For example, let's say we have figured that one particular server can only at best can handle thousands requests at a time, because again we are constant, and then we basically scale it horizontally, right? We add more servers to serve our customers. But what if this same resource would be able to serve 2,000 requests? That would be a huge set, right? So that's what we want, because otherwise, let's say what happens in ideal real world, when a request comes to the server, so this is a thread is allocated for this particular request, and this thread doesn't work all the time. What happens is this request probably this when a request comes, it probably needs to talk to a database, right? And it probably needs to go to talk to another microservices. So let's say a thread A initiate a connection with the database, and database definitely takes some time to process, right? It let's say it probably take like 100 milliseconds. Let me just ask MS 100 milliseconds. So while this database is processing, this thread A is basically waiting. It's not doing anything because it has to get the result, and then it can process further, right? So what happens is this 100 milliseconds, the thread A is basically staying idle. It's not doing anything productive. And at the same time, it's a valuable resource because we cannot have many of them. Since we cannot have many of them, and we are basically wasting our valuable resource, right? But what if this particular one could do is, while it's waiting, it can just serve other requests. When this database will send a response, and immediately another one pick that pick that result and start processing further. That will solve a lot of problems. So that's not what's happening with this traditional way of doing threading. So what happens is these one is, first of all, we are limited by the we're constrained by the number of threads we can create, and secondly, they are basically staying idle in many cases. In most cases, I would say, let's say 80% of time they're just staying idle. They're not doing anything. So these are the problem. And how do we solve that? So that's why the interesting things comes, where is the solution and implementation, which is called Project Loom. It has been Java team, the engineering team and Java community has been sort of engaged or developing this one for a long time, and finally they have come up with a solution called virtual threads. So what happens is, let me just give you a background, then I'll go into the how we can create virtual threads and other things. So what happens is with the virtual threads, now we can say Java has two kinds of threads. Two kinds of threads. One is traditional threads, like the way so far what I have shared with you. Traditional thread. Sorry about my spelling. And we have now another kind of threads, which is called virtual thread. I'm gonna quickly go over with it, how it works, and then I'll show you how to create virtual threads and how can we use it. So traditional thread has some few other names. You can call it native threads, classical threads. And there is another name which is in JDK they have been using, which is called platform threads. Okay, so you can call by any names, all of those are correct. And there is another thread which is called virtual threads, and you can also call it user mode thread, or we can just call it virtual thread. I mean, that's fine. So what happens is these virtual threads are cheap. We can create a lot of them, but the intelligence behind it is there is a thing called fork join pull, right? We all know about that, right? JDK 7 comes with this fork join pull. What happens is this pull creates a it's a pool of threads, but it's not the limit number of thread is basically the runtime runtime dot, sorry, I probably have to go over here, runtime get runtime available processor. So the number of processor you have are the let's say X. So basically the something went wrong. I don't know what happens. Anyway, oh, so this line is unreachable by this because we have a while loop over here. Anyway, never mind. So what happens is basically if we have like 10 processor available in this machine, this fork join pull basically create 10 threads. So this 10 threads is going to work all the time, right? So what happens is we'll create a virtual thread. Virtual thread is basically a Java construct. You can think of it as a Java object, like regular Java object. You will create that regular object, and you'll give a task to it, and in this 10 thread, let's say these 10 threads are in this fork join pool, and they're always running. So one of these virtual thread is going to be mounted on top of this fork join pool threads. Let's say from here we take one. Let's say we take one, and in this thread, we're going to mount a virtual thread, basically, let's say. And this virtual thread is going to start working. And when there is an opportunity, there is a situation like IO operation. For example, database call is a IO operation, right? Anything with IO. IO operation, sleep is another of them. So if it sees a IO operation, which takes time, right? So it can unmount itself. It can EL itself from the running thread, which is the traditional thread, basically. So what happens is, database call is definitely a network call or IO call, right? So when it sees this, virtual thread unmount itself from this traditional thread, which is inside the fork join pool. So this thread is now free again, and it can immediately pick another virtual thread. So while this virtual thread is waiting, it can wait in the heap like just another object. This traditional 10 thread is working on another virtual thread. That way, we can create many of them, like tens of thousands of them virtual thread, and they are not wasting my CPU, because when they're waiting to get a result, they can just stay idle. And while the traditional threads, which is, let's say, our the threads inside the fork join pool, they're always working, and that gives us the efficiency. And since we can create many of them, like we can create millions of them, we can now achieve the high throughput that we're aiming for. Because now that if we have like tens 2,000 requests, we can just create 2,000 virtual thread cheaply. So that's the beauty of having virtual thread. That's what happens actually. So now moving on, let me see what I have in this slide. Okay, so how we can create virtual thread. That's what I'm going to show you now. Let me know if you have any questions so far. I'm basically trying jumping ahead a bit because I just saw I have already spent half an hour on this topic.
No problem, Baldur. You can take time. Our audience will wait. No problem. Take it as per your convenience.
Okay. So let's go ahead and see how can we create virtual threads. There are several ways. One is, we can call, there is a builder pattern over here called thread of virtual, and we can just call this start method. And if we pass anything inside, let's say, hello world, then this, anything inside this curly brace is going to be executed by this virtual thread. And that's it. This is how we create virtual thread. And if we want to get a reference, we can have a reference over here. And let's see if it runs. And also, if we want to, print to see that if it is indeed a virtual thread, you can just call thread.current thread and then print it. So one thing we have to keep in mind is virtual thread and daemon thread. They are daemon threads. So let me show you why I'm saying that. So if I run it, you can see there is nothing in this console. The reason is, main thread starts from here, and I just asks to create a virtual thread, and then that's it. Main thread doesn't have anything else to execute, so it dies. And since it's a daemon thread, the virtual thread one, this particular one, and it also dies because the parents all die. So we have to wait for wait to finish this, and that we can do the join. So we definitely have to keep that in mind while demoing it. Now we can see this is the hello world printed with the virtual thread, and you can see there is a name over here, and it's a virtual thread, and it's standing on a fork join pool. And fork join pool can have like the number of processor we have, which is so it basically took worker 1. So that's one way of creating threads. And if we want to create a lot of virtual thread and then we don't want to start them immediately, we can call another method, thread.virtual unstarted. So it's the same thing, but it will not start immediately. You have to call start method explicitly. For example, this is unstarted, right? So you have to call it, whenever you feel you need it to call, start these virtual threads. So one thing you notice that this thread, all of them are same, right? The virtual thread is basically internal construction, and the class that we used to use for threads remains same. So the virtual thread is basically, internal construction, but the class that we're going to use is same, which is threads, and it has all this property that traditional thread has. So it gives us all this benefit we had with the traditional thread. For example, observability, we can use the way we used to debug and all those things, the way we used to view stack trace. It remains the same, although the internal it's a bit different, right? But from a developer perspective, it remains the same. So that's the beauty of it. And yeah, so that's two ways of creating virtual threads. One is started, another is unstarted. And sometimes it happens that we don't want to, we always want to start the virtual thread immediately. If that happens, we can just call thread.start virtual thread. There is another method over here, which is factory method. You can just, this one definitely is gonna start immediately. You don't have to, it will not wait, it will just start immediately, right? So these are 3 ways we can create virtual threads. And there's another way, which is, let's say you have a traditional thread pool in your existing code base and you want to migrate from that. So they have added a new method in the executors frameworks. So let me show you that as well. Let's say for executors new fixed thread pools, let's say 10. So you probably have this kind of construct in your existing code base, right? So you submit task, right? Or you submit either a runnable or callable, whatever the situation you have. So it's a task. So basically, if you need to return something, it will be a callable. And if you don't need to return something, it will be a runnable, depending on your situation. And then it will just give you a future. So you may have this kind of code in your whole code base a lot. Now, how do we, refactor it and start using virtual thread? So that's why they created a new method over here, which is basically makes our life a lot easier. New virtual thread task executors. What happens is with this one, we don't have to do anything else. All the code remains the same, but whenever we submit a task, this particular task is going to be executed by new virtual threads internally. So we don't have to do anything. So if we want to switch from existing code, which has this type of code structure, we can just change one line, and that's all we need to do. So these are the ways we can create virtual threads, and yeah, that's all about virtual threads. And let me see what else I have in this slide. Okay, so I show you the demo, and before going into how it was implemented, I need to show you some, what do we say, some things or downside that came with. I won't say downside. We just have to be careful about it. Okay, so before going into that, let me show you another demo. But before I move to the demo, do you have any questions so far?
Yeah, I have a question.
Go ahead.
Okay, so from a design decision perspective, when will you go for virtual threads? And I mean, what are the scenarios that you would choose to use virtual threads?
Okay, excellent question. So I haven't covered this out. So what happens is virtual thread is really suitable for IO intensive work.
Okay.
Works. So whenever you need to call a IO operation, for example, a network call, you need to wait for data to arrive, the result to arrive. You're going to use virtual thread. For example, you need to call a microservice, you can use virtual thread. But for CPU intensive work, you are not going to use virtual threads, because what happens is, so that's why the internal is a bit important to know, which is so let me go back with again over here. So what happens is, let's say there is a thread over here, A. Let me rename it T. That way it sounds good, which is T is threads, right? So this T is a thread, and it initiated a database connection query, right? And this query is running on a different process or different machine. It depends. But to get the result in this T thread, it takes some times, which is 100 milliseconds per second. For let's say 100 milliseconds, it could be far more or or less. Never mind. That's not our discussion. Anyway, so it takes some time, and while it's executing in a different process, this T1 basically staying idle, right?
Yeah.
So this T doesn't do anything, and this particular problem, which is a problem, right? It's a valuable resource, and we're wasting it, and it's staying idle. And so that's the problem we're gonna solve it. So what happens is, this is a traditional thread over here in the fork join pool. Let's say this is a T, and it calls IO operation it's a database. What happens is, we'll wrap this IO call into a virtual thread, right? We wrap that call into virtual thread, and that's it. And internally Java, what it would do is, this virtual thread is going to be executed on top of this fork join pool, which is our traditional thread, native thread.
Okay.
So this virtual thread is going to be mounted on this traditional thread, and it will start executing. And the point it's the IO operation. It will invoke the IO operation, and then it will EL itself. I mean, the virtual thread is going to be removed from this traditional thread. So this thread is now again free and it can execute another thing. So this only happens when there is the IO operations or there is a waiting involved, right?
Correct.
But if you have a CPU intensive work, which is a computation, there's no need to. There is no clue. Or the virtual thread has no clue that I need to yield myself because I'm computing. I don't have to wait. So then it will not yield itself. So this means is the running CPU intensive work on a traditional thread on a virtual thread is pretty much same. So we are not getting any benefit.
Correct.
Right. So the highlight is from this is if we have to call a IO operation, it could be network, microservice, whatever you can think of. Then I will definitely use virtual thread. But if you a CPU bound work, CPU intensive work, I'm gonna go ahead with this traditional way. I can use there is a different way of doing CPU intensive work, right? For example, also using for example we can divide and conquer and some other kind of things we can do, or also we can use parallel stream or if we want to use other way. It depends on us, but we just have to put that distinction. If it is IO bound work, I'll use virtual thread. If it is a CPU intensive work, I'm going to use the traditional one.
Thank you.
Makes sense?
Yeah, thank you. Yeah.
All right. So let me go ahead and show you a few other demo. Let me see if I have those. Okay. So over here, there is it's a very basic crawler that I've written. What happens is, let me explain a bit over here. So what happens is you give a URL over here. So it will go into that URL and try to read this whole page. And if it sees any URL inside that page, it will add into a queue and it will start processing again. So, and we have a limit. For example, we want to, maximum we want to, search 100 pages. And then that's it. That's our limit in this particular crawler. So very basic. It just goes, and if I can show you the code, what happens is in the run method, if this URL contains the key, not contains the key, then it will go into this code block, and it will just call a it's a basic way of doing things, which is open connection and see the content type is text, and then there is a framework called JSOP. JSOP is basically connect the URL and read all this content, text content, and it just goes into see if there is an href there. If then it just put into this queue and keep doing these things. So we're gonna do this two-way. First of all, we're gonna do our traditional threads, which is we're gonna create a fixed thread pool. The comparison is a bit deliberate over here. So we're gonna take the number of threads, which is the number of CPU core we have available. So over here, I assume in this computer we have 10 core, so it will probably 10 thread. But it's a dynamic, so I don't have to worry about the exact number. So what happens is I've created executors, and then we started, we started executing it. So far, it's a simple code. I can give you the code later if you want to explore what it is. But high level is it just keep on fetching the page, and it sees the content, and if there is a URL, it just put into the queue so that it can process again, and it will finish once we have processed 100 pages. So that's what it does. And then I wanted to do a basic what do we say, basic performance measures. It's a pretty basic. Ideally in real life, this is not how we're gonna measure the performance, but for the demo I think this is fine. So let me run this and let's see if it works. Sometimes it doesn't. So You have to stay with me. It takes some time, And as you can see, it crawled 105 pages, and the throughput is like around 8.9. So page per second, right? It's not a impressive one, but this is how much we could do with the traditional thread, the amount of processor available. So I mean, it could do better if we improve, add more threads to it. Let's say if we add 100, it will dramatically improve, right? Throughputs. But again, the purpose of this demo is we're gonna use the same amount of traditional thread and see with the virtual and the regular one how much difference it makes. So let me comment out this one. And now we're going to use virtual threads. So let's see if we have some improvement over here. Okay, so what happens is over here, probably, so I'm sending a lot of requests, and Wikipedia is basically preventing me. That's the reason why I'm getting a lot of errors. Despite all the errors, you see there is a huge improvement, right? 81 and 8. And interesting thing is, in both cases, the amount of native thread we're using the same, right? Which is, let's say 10 core I have. So the native thread, we're using the same amount of native thread. But over here with the virtual thread, we have a huge improvement in terms of throughputs. So this is the difference between traditional threads and virtual threads, right? We can have huge amount of that. And I probably didn't show you the demo how many virtual thread we can create, right? Maybe I'll show you in a minute. Okay, so this code is perfect, but it has one particular problem. So let's go ahead and identify that. What I'm gonna do is I'm gonna configure it in a way. I'll add a VM operations and VM flag, and I'm gonna run it again. What happens? Let's name it 2 or with flag. Okay, so I'm gonna run it again. Let's see what happens. So okay, so that's all I needed. So as you can see over here, when it start doing in this status, there is a thing called on pinned. So this is the problem. Let me explain what is the problem basically. What happens is it's a limitation, I would say, of virtual threads. If you have a code block that use synchronize keyword, or it call a native methods, it pinned itself on this carrier thread. So what happens is, like I said, right, virtual thread runs on top of a platform threads, which we call a carrier threads. It pinned itself, so it doesn't yield itself while it's working. So that's a problem, right? We want to, we want this. What do you say? We want our traditional threads, virtual threads, not to be pinned with a particular threads. Because if it's removed, it goes away from the traditional thread, we can run another one. So that's why we achieve overall scalability, right? So if we have this situation where the virtual threads pinned on top of a carrier thread, that's a problem. And this is what's happening in this code. even though we are getting dramatically better performance, but still it gets pinned for for a few seconds or for a few milliseconds or a very short amount of time. So why is that? The reason is we're using over here a library called JSOP, and internally JSOP probably use synchronization keyword and all those things. I haven't checked, but from the log stack trace, we can pretty much see that it got pinned, right? So it got pinned somewhere in the code. So that's the problem. So that's a kind of limitation. And in this JDK library, they have removed a lot of places, removed all this synchronization keyword, and started using the lock, which is lock. You can use re-entering clocks or something like that. So if you use lock and instead of synchronized keyword, then you are going to be fine. And perhaps you shouldn't use native method as well. So these are two places virtual thread doesn't perform well. If the amount of time it's going to pin is longer, but if it's a very short amount of time, that's all. This is fine as well. So what we're going to do is we have another color over here, and this one doesn't use JSOP. It's use a traditional. Sorry, it's use a HTTP request, HTTP client that comes with JDK 11 by default in the Java, and it doesn't use synchronization keyword. It probably use the lock and other mechanism. So if I run this code, it will be a bit faster compared to the JSOP version. So let's see if I can see. Okay, so what happens is it sends too many requests, right? That's why there was an error. Yeah. So what happens is HTTP client, probably there is a configuration that it can, at a point of time, it can send a fixed amount of request. But since we can create a plenty of virtual thread at a short amount of time, so it's sending a lot of requests. So that's a problem. That's why it's saying too many requests, too many concurrent requests streamed, right? So again, nevertheless, that's a problem. That's a problem because we cannot. If we send too many requests to a particular resource, probably it will be overwhelmed. That's another side effect of having virtual thread. Within a short amount of time, we can create many. Let's say even creating millions thread, it's like easy now. Anyway, but still we see a lot of errors over here, but still the throughput is much better, right, compared to the other one, which is 81 over here. It was 81, and then when we remove the pinned situation, we also got a huge improvement. So that's a limitation. We have to be careful. So if we write a code that's gonna execute it by virtual thread, we have to remember about two things. Our code shouldn't use the synchronized keyword, or the library we're gonna use shouldn't use the synchronized keyword, or we have to make sure that it doesn't have any native call. That's the two things we have to keep in mind. Now, with this new, this is a new error, right? So this is a new problem we are facing over here. Since earlier we could control the amount of thread we could have, like with the fixed thread pool, thread pool will have like thousands, or we have a fixed amount. Now virtual thread is pretty cheap. We can create millions of them. And let's say I have a database that can only handle 100 concurrent requests at a time. Now, if we send 1 million requests to this database is going to be overwhelmed, right? So that's a problem. So how do we solve that problem? Previously, when we used to have we didn't have virtual thread. We just had have a thread pool. Let's say we will create a thread pool with 100 threads, and at a point of time we'll have only 100 threads. So the problem would not be there will be no problem, right? But now we have a huge flux of virtual threads, and it's gonna call a lot of instantly. So that's a problem. So we can solve this problem by a thing called rate limiting. We know that term, right? So basically what happens is, if we can limit the amount of threads is to a particular resource that has a limitation, we can rate limit. And I have a demo for that as well. Let me see if I have over here. So let's say I have this mock database, right? And I have just, for the sake of demo, I have created a mock database. And I can have only 10 connections at a time, at a point of time. So what I would do is I'll create a semaphore. So let's say this is a semaphore. It's an existing, class. It's been available since, I don't know when, 1.5. It's available since 1.5, Java 1.5. So that's already an existing class. We can just create a semaphore with a permit. So the idea is, when a thread comes to this method, we'll acquire the permit from this semaphore, and then we'll do our work, which is over here. We are creating a connection, and when we are done, we are just releasing the semaphore. So that way, only 10 threads at a point of time can get into this particular resources. So if we have this sort of limitation, where, for example, in our earlier demo, we were seeing that too many requests. So if that kind of situation happens, you can restrict our the amount of thread or amount of concurrency we can have with this semaphore. So yeah, that's how we do. Basically, it has two methods: acquire and release. So we'll first acquire it, and then finally we release it. And I have a test over here as well. So what happens is, I'm gonna create thousands virtual thread over here. So I'm gonna try to submit thousands of them to get the connection, hold of that connection. And but the requirement is, at a point of time, we can have only 10 threads for this get connection methods. So yeah, that's that. So the test is simple. When we're gonna get into this get connection method, we'll increment the counter, and once I have get this connection, I'll just decrement it, so that it is always consistent. And there is another atomic integer which is keeps the maximum number of count. If I run it, even though I'm sending thousands, I'll see this test is going to be passed. Even the test is passed. I don't see any problem over here. So these are the two things we have to keep in mind. One is spinning problem. One is, if we need to rate limit, we can use semaphore. So yeah, that's pretty much the demo I had for you all. And let me know if you have any questions.
Can you please share the link for this sample code? It will be useful for the participants.
Sure. I'll definitely share. So I have. In fact, I'm writing articles for, I'll write article for each individual topic that I have shared over here. So I'm probably going to share that as well. That way, for example, this particular one, I can immediately share with you all. Let me show you. So this is the same article that I have shared over here. And the demo I have done over here. It's the same article basically, so you can just read that if you want to, go into depth. So this is going to be a series. So first of all, we'll compare the traditional thread with the virtual thread, and then we'll have a pinning problem, and the third one will have a rate limiting problem, which is going to be used by semaphore. So let me share this first one. Where do I share? Sure. So
just a few words, just for others' sake, in case if you are not aware of it, can you go to the link, Bazlur? So Fujay is a community of Java user group members and passionate Java developers across the globe. In fact, we got to know Bazlur through Fujay. It's a great community, and any Java developer will find a lot of informations like this in Fujay. So please go and check it yourself. I found it very, very useful personally.
And also I'm doing a interview over here. You can see with the lot of starts from the around the globe, and I have done a few over here. You can see this is the Simon, and this one with the K Hortzman, Sebastian, Jacob Jankov, and Nicholas. I'm doing it. This is Chris Newland. And they have a lot of insight to share. So if you are interested, you can read this interview series as well. So over here, we have a lot of interviews, and there will be a few more in the coming month. So anyway, so that's all I had. I wanted to share this implementation, but I guess it will take some more time. So I'm gonna skip it for this time. Maybe in future I'm gonna share this part as well. So just to give you a highlight how it works internally. So this picture maybe give you a bird eye view how virtual thread works. So in the operating system, we have like operating OS thread, right? Native thread. And then we have a Java thread, and we have like one mapping with that. And then in the Java layer, in the JVM, we have a for example, which is a scheduler for our virtual thread. And virtual thread, we can have millions of them. And virtual thread with this carrier thread have a one-end relationship, basically. So one carrier thread can run multiple virtual thread. At a point of time, definitely it's going to run one. So virtual thread will, the JD scheduler will schedule one, and it will be mounted on this carrier thread. It will start executing, and when it sees a opportunity to yield itself, it will yield immediately so that it can execute another virtual thread. So that's how we get the scalability part. And I'm going to skip the continuation over here for today. And there's similar concept in many other programming languages. For example, Kotlin has coroutine, Go has GoRoutine, JavaScript has async wait, Python has generator, Ruby has Fiverr, and finally Java has a thing called virtual threads. There is a distinction between the async wait and the Java one. Many people ask why Java didn't go with this route, which is async wait. The problem is, the problem with async wait is if a method is async method, from a non-async method, you cannot call it, right? You have to make it turn it async as well. So there is a two type of method. One is async and another is not. And these two, like water and oil, they don't mix. But with this, virtual thread, you don't have those problems. And in fact, there are a lot of benefit with the virtual thread over here. I have mentioned a few over here. Technically now we can have millions of virtual thread. Virtual threads don't consume CPU while they are waiting and sleeping. They just occupy the heap. And we now can achieve higher throughput on blocking IO. Virtual thread gets automatically suspended. So that's the whole point. And the biggest benefits of virtual thread is, I would say, we no longer have to use thread pool. So maintaining thread pool is also a sort of headache for Java developer, right? You have to tune it, how many threads we can create, you have to experiment it, right? And now we need to go away from that habit. We no longer need to create thread pool anymore. We can, whatever task we have, we can create a virtual thread and give it to it. And this task can be a short-lived, right? So that's the idea. The
I think
basic
Salam
idea
has
is
a question. Salam, I think there's Salam, please go ahead.
Yeah, I just wanted to, yeah. So first of all, thanks a lot for the wonderful presentation. Right. I just have a very specific question on the stream and the parallel method, actually, right? So parallel method is kind of spans another thread, etc. Right? So is there a way to specify that as a virtual thread, or by default is it considered as a virtual thread? Or how that goes actually with the parallel stream. Do you have any
parallel stream
idea about
is parallel stream is going to use a okay. So what happens is there is a common pool in JDK, right? When yes, that's definitely used for fork pool, but for virtual threads, it has a different fork pool. Basically, these two are not the same. So for parallel, parallel processing, it's going to use the common thread pool, which is basically another fork pool. But for virtual threads, it's just another fork pool. They don't share, first of all, and second is I would say for parallel streaming, I would say it's a more of a computation related work, right? I would probably not recommend such computation work using virtual threads. That's not a point of having virtual threads. I hope I answered your question, but if you have more confusion, I can definitely try.
Yeah. Got it. Nice.
All right. So there's another benefit
the
of
other question I had was about
sure.
So in your diagram, you just showed us like how the native thread and also the FIFO was maintained actually, right? So there's a guy in between maintains the virtual thread for you, right? So let's say that I have 1,000 native pools and then 1,000 virtual pool, right? So virtual threads, right? So will there be any difference in terms of performance while running the same amount of virtual thread versus the same amount of the native thread? The reason why I'm asking that is there any kind of overhead of running kind of in a switching mode by using this FIFO here?
So that's a good question. I definitely did not experiment this idea, but probably we have to figure out that. But from the high level, what I can say is, from the high level, this virtual thread is hidden from the operating system scheduler. Operating system scheduler basically don't see virtual threads; they only see carrier threads, right? So if you have native threads, so basically if you have 1,000 native threads, the operating system is going to schedule them, right? For virtual thread, we'll have a dedicated fork pool, which will have the exact amount of processor you have available. For example, if your computer have 10 processor, it will only have 10 of them, right? This 10 is responsible of executing all these virtual thread. The number, how many number you have, it doesn't matter. This 10 is going to be executed, all of them. So now, on top of this 10, if you have 1,000 another, then the OS scheduler is going to need to schedule 1,010, basically. Makes sense?
Yeah. So basically, the reason for asking that is like, so in many cases, we may not be running like millions of threads actually, right? Maybe like few hundred threads based on and for the most of the use cases for that matter. Right. So is there any kind of advantage I would get by just using the virtual thread versus the non-thread? I mean, I do understand that this gives you a lot of code maintenance. From the code maintenance perspective, the libraries are clean now, etc. So keeping that aside, the real performance of comparing the old versus the virtual thread, will there be any?
I would argue that you're going to get some benefits using virtual thread over traditional thread for IO intensive work. First of all, the reason is just let me give you an idea. So now let's say you have 100 traditional threads, and these hundreds are scheduled by operating systems. I could be wrong, but I'm just this is the thought it's going on in my head. Which is basically, if operating system needs to schedule 100 threads versus it needs to schedule 10 threads, which one is better?
I think Yeah, I get it actually. So again, at any point in time, operating system can just run a limited number of thread actually, right? And then you have that switching mechanism in between, right? So that's why I'm just a bit worried, like, whether will there be any benefit of that actually, right? Probably that's something we can explore.
Yeah,
Yeah,
sure. You
with
can just
solid
try
some
out and see the
etc. Yeah.
difference, see the differences. But
Yeah,
I would
sure.
argue that if you have IO intensive work, if you use virtual thread, it will give you a better performance. But again, depends on the number as well, right? If you have, like, if you have, for example, if the number is large, then you will probably get more benefit than if number is
Yeah,
small.
certainly when it comes to the more number of thread, etc., certainly the virtual thread is going to win because it's giving you a lot of flexibility for you,
Right.
right? But in terms of the actual running, and if I don't have many threads to run, what exactly we benefit out of this? Actually, that was my original question. Yeah, just to be specific. Yeah, okay.
Sure. I'll definitely explore your question, but on top of my head, I would
Thanks a lot.
argue that virtual thread is probably going to give you more benefits compared to the traditional one. Like in the demo I showed you, right? With the same amount of traditional thread and with the virtual thread, we get overhead with virtual threads. Anyway,
Actually,
moving
I'm trying
on.
to
I'll
combine them
definitely
together, Bazlur. So,
Yeah.
sorry, I'm just trying to take it from both of your versions. Shall I take it something like in a traditional web application where there will be highly concurrent request and we do not even predict how many load we will get. There, virtual thread seems to be more appropriate for me. Whereas if I'm considering
Yes.
traditional batch process where I know that this is my system resource and this is the
Right.
concrete activity that I'm going to do, my platform threads will be more useful. Is that a fair kind of an assumption?
So if I know, if I know that how many batch operation we're gonna do beforehand, I would still argue that virtual thread probably gonna perform better. But again, we need to experiment that. I have never experimented this idea. Yeah.
But one thing is, as the programming model is same, experimenting,
Right.
switching between these two should be relatively a cakewalk, right? We can switch it and then we can check. Yeah.
Right. You can just try out. For example, I would assume that when you are doing your batch processing, you probably have executors, right? And in the executors you have a thread pulse. That's how we do it. Just switch one line and see the differences.
Yes.
All right. So moving on. This slide I always show you. It's just a fun one. We have two code over here. One is the top one is use reactive programming, and the bottom one is basically traditional imperative programming. And if have to choose between these two way of doing, both of them does the same thing basically. Both of them, the result of output is same, remains same. But if you are to ask which one would you prefer, which one would you prefer? So there's a question for all of you, for the top one and the bottom one. This is a fun question I ask on every presentation in the end of the session.
As a modern Java developer, if you claim, then people will always prefer the first one. That it should be declarative style of coding.
Okay. Anyone else want to ask? Answer. Okay, so let me rephrase this question. First one is basically it's a reactive way of doing thing. You have to, Spring. It's written using a Spring reactive framework, and the second one is basically traditional. It doesn't do anything fancy. So let's say if I have a junior programmer, joined in your team, and you have to explain this to which one would be easy for you to explain?
Second one.
All right. So the benefit using virtual thread is probably this one. Your code becomes straightforward. You can write a traditional straightforward imperative program code that easy to understand, and you probably don't have to explain anyone. You can just write it, and the learning curve is pretty zero here because you don't have to learn anything new. You can just you traditionally you can write for loop and you can start creating a virtual thread. But the same benefit, if you want to get the same benefit what virtual threads offer with other alternatives, which is reactive is one of them, then you have to learn a few things. First of all, you have to learn a new technology, which is reactive, right? Reactive programming. It's also so there is a learning curve, first of all, and secondly, you also lose a lot of things with this reactive programming style. First of all, one is the debugging is become difficult, and if you say stack trace, this stack trace will give you nothing, because so those are things you are gonna lose if you use reactive programming style. But on the other hand, if you start using virtual thread, you are gonna get all this benefit, which is, first of all, it gives you much more better readability. It's easy to understand, easy to code, and easy to debug, and it will give you a good, nice stack trace if you need to read if something goes wrong. So these are the benefits basically on top of the other alternatives we have in the Java ecosystem. So I just wanted to share that in the end. Someone was saying something. Sorry.
I was saying, like, debugging in reactive is a big pain. So the second choice would be much more apt.
So yeah, so right. So that's the whole point of this slide, basically. Yeah, with this virtual thread, you can now go back to your traditional way of doing thing with all the benefits you had earlier, which is debugging, stack trace, all those things. Yeah, and also now the benefit of scalability, which is we didn't have virtual thread, that's why we invented other stuff, for example, reactive programming, right? Now probably you don't need them anymore. And some of the frameworks also started integrating virtual thread. Spring Boot also started, Heligon, Nima, Quarkus, and I have recently seen, I did not update this slides, but some of the other programming framework, even Jakarta started implementing virtual thread. So soon you'll be able to use virtual thread without even knowing anything. It will just work out of the box. Go ahead.
Yeah, but the Spring Boot, as much as I know, the current one, that is 3, minimum version is 17. So if people are using 17, they will not get the benefit of virtual thread. Correct me if I'm wrong. They need to use Spring Boot 3 with the latest version of Java.
Yeah, that depends on what JDK you are using.
Yes. Yeah. Right. If you want to use virtual thread, definitely you have to go with JDK 21, which is the latest one.
And Helidi and Nemo is a very different approach compared to others. It's a very interesting approach, but rarely we see someone knowing about this framework. We are even struggling to find speaker for that. The beauty about Helidi and Nemo is it has built its own web server implementing virtual threads. It's not using Tomcat or it's not using Netty. They have created their own web server using virtual threads. So obviously for microservice use case, it's a far better choice. But the problem is, rarely we find any community speaking or something like that. It is still a closed resource. Not many people know about it.
It's still
the community support is not there in that one.
Yes.
Probably that I would not argue with that. But they have started everything from the ground up with the support of virtual threads. So interesting. Obviously there are plenty of framework out there, right? But if you see compare the market share, you will definitely see Spring is probably the most used one, and other people just use other framework for various reasons, right? But the market share wouldn't be that high. I would say it's 80% people would choose Spring Boot, and rest of 20% probably 50% will use Jakarta, and that the rest 5% probably use other framework like Workers, Helidon, and all those things. That's my thought.
Yeah, that is true. I am personally a Spring Boot fan. I use Spring Boot quite heavily. Spring Boot comes with a safe choice. Say, for example, whatever choice that you do, even if there is some problem, we can be rest assured that it will be taken care within a couple of months.
Right. Yeah, a lot of people use it, and a lot of community help. And since we have more programmer available for Spring Boot, it's definitely a safe choice, right?
True.
So that's all I
Another thing is
have.
the securities.
Yeah,
Good,
definitely.
good.
Definitely. So there are a lot of API changes happen to accommodate these virtual threads internally. I'm gonna just skip it because I can just share the slides. So what happens is inside the JDK there was an overwhelming change happens internally to accommodate this virtual thread. So the idea is how virtual thread knows that it needs to yield itself, right? So basically through an IO library. For example, it could be a input output system. I'm not sure if they have changed internally of input output stream, but I'm just saying in the input output stream, when you invoke input output stream, that means it's IO operation, right? So that's when virtual thread knows that I need to yield myself. So to accommodate that, they have in the JDK they have changed a lot in lots of APIs. So pretty much they tried to all the IO point in the JDK library, they change it so that they can accommodate virtual threads. So that's why it took a while. For example, it did. Oh, okay. So I have added this. For example, to avoid pinning virtual thread, these libraries also rewritten so that it doesn't use synchronized or natives. So that they updated their internals with the locking mechanisms. Anyway, there are a lot of changes in debugging architecture as well to accommodate virtual threads. I'm going to skip all of them. I'm going to share this slide with you all, and there's two code that I quote some end of this my slide, which is virtual threads are chief enough to have single thread per task and eliminate the many of common issue with writing concurrency code with Java. So if you have a small task, traditionally you used to submit to the thread pool. Now you don't have to, you can create just a virtual thread. And there aren't any new API you have to learn, but you do need to unlearn many habits such as using thread pools to deal with resource contention. So you don't need thread pools anymore. So that's the highlight of this code. So that's all I have for you. And I write a lot. There is a new newsletter that I have started recently, which is the Coding Cafe. Over here, I shared a monthly newsletter and often a lot of article in between. So recently, I have started a new series called Concurrency 101. So what happens is over here, I'm trying to write a small piece of article, small, easy to digestible, so that it doesn't take a lot of time, 2 minutes perhaps, and I try to share a concept, ideas of concurrency related concept in that article. So if you want to stay connected with me, you can take the screenshot of this QR code, or you can just search this newsletter in the LinkedIn. Apart from that, you can find me, let me share that, you can find me over here in the FOJ as well. You can find me on Twitter, where I share a lot of content, and definitely you can find me on LinkedIn. So that's all I have. Thank you, everyone. You guys were a very attentive listener, and I hope you enjoyed this session. And if you have any feedback, feel free to share with me. Thank you.
Thanks a lot. It was a great session.